Hello everyone, good morning and welcome to Open Source Summit. In this talk we are going to see how Zephyr RTOS is used or act as a electrical vehicle supply equipment. In other words, in short, it is called as an electrical charging station, and using the open standard called Open Charge Point Protocol. So my name is Saravanan. I'm a part of Linumiz. I'm working as a software engineer, or the embedded software engineer at Linumiz. Over 13 years of experience in the Linux, working in a Linux. I'm a developer and a contributor to the open source projects like Linux kernel and Zephyr RTOS. About Linumiz, it's a software servicing company which provides embedded software development and consulting and training in embedded Linux and Zephyr RTOS project. So we do servicing in the range of bootloader development and then kernel development, new boot support packages, and also the device driver development. I live in Berlin. Okay. Here is the summary of this talk. First, we will check what's an electrical vehicle and how the current state of the infrastructure, charging infrastructure, and what is the limitations currently having, and then how does Zephyr RTOS helps to improve the limitations for achieving the better charging infrastructure. And this talk is primarily focused on the Open Charge Point Protocol. It's an open standard specification, so we will look into the what is Open Charge Point Protocol or the OCPP, and then we will have a brief look into the specification internals. After that, we will have a look into the OCPP implementation, the native implementation of the stack and the Zephyr RTOS, and how to consume it in the application layer. And after that, we will have a look into this electrical vehicle supply equipment standards, which is mainly used to connect between the charging station and EV for handshaking and delivering the power. And finally, we will look into the current state of OCPP in the Zephyr and the future work. Okay, so electrical vehicle is an emerging market because of its advantage of environment friendly, but there is a limitation because of a lack of charging infrastructure. So electrical vehicle supply equipment or the charging station is simply called as a charging station, which is used for the supply of electricity or the energy to the electrical vehicle which utilize that to the battery charging. In comparison with the gasoline vehicle, like petrol station, which will takes a few minutes to refill the fuel, but one of the limitations with the electrical vehicle is the amount of time it will take to recharge the battery is very huge, and also it occupies the parking space until it gets recharged fully. So, but one of the advantages with the charging station is which is a portable, and it can be installed, easy to install in most of the parking place. So is it really need to be installed in the parking place, because like we cannot make it installation in the petrol station or the gas station because we need a more parking lot. So the better place to install the charging station is the existing parking place where we can utilize that. So in the nutshell, we need a more and more lightweighted distributed networks, so where we can employ that instead of handling the bulky machine which can handle the multiple port, like 100 ports of charging vehicle, it can handle it. So we really need a distributed network where we have the parking lot, where we will have like the highways or else the hotels or even the working office space environment. So we have seen, so what is the limitation, and what we really need is a distributed charging infrastructure, and how does the Zephyr gonna helps with this distributed charging infrastructure. So microcontrollers are more suitable for the lightweighted applications, and then for the microcontrollers, we obviously have one of the choices, Zephyr RTOS, which has more advantages in terms of its supports a multiple Ethernet interface, and then the other interface which we'll go and see. The Zephyr RTOS has its advantages, like it has a native implementation of TCP IP stacks, and then it can be directly used to the Ethernet controller. And apart from that, we can use the internet infrastructure for the Wi-Fi controllers, and a lot of Wi-Fi controllers which supports offloading, which means we can send the payload, and then the TCP or the IP packet will be framed by the offloading controllers. So we have the support in the Zephyr RTOS for the offload socket option also, so which will reduce the burden on the microcontroller, which can focus on the application side. And one of the requirement for the EVSE is, like, when we are going to install the charging station in the highways, like where it is in the remote areas, we have a lack of internet infrastructure, so we can use the modem as one of the internet-facing interfaces. So Zephyr RTOS supports a modem like one single die solution like NRF, where we have the application processor application CPU, and also the modem can coexist in a single die. Otherwise, also the Zephyr supports other external modem which works on the CMUX or the PPP or AT commands. And then Zephyr RTOS itself supports the variety of architecture, supports like Extensa, RISC-V, ARM, and also the because of that, we have a more and more platforms supported. So if you want to go proof of concept, which will be helpful, like the existing platform with the Ethernet support or Wi-Fi can be used as a proof of concept before going into real product use case. So as a EVSE really wants to measure how much the power it is, how much the power or the energy which is delivered to the EV, the charging station should employed with the energy meter. So most of the industrial energy meter supports digital communications like Modbus or Modbus, and then the UART or other serial MBus modules. So thanks to Zephyr RTOS, which supports the native support of the Modbus as well. And at the end, we are going to have the support for the Open Charge Point Protocol native stack in the Zephyr as well. So collectively, we have a lot of advantages why we should go for the Zephyr RTOS, how it would be helpful for improving the charging infrastructure. In addition to that, we do have a RFID reader, which probably with the NFC stacks, and it's going to be integrated or the merge soon into the Zephyr RTOS. So we have seen so far what is drawbacks in the charging station, how does the Zephyr RTOS going to help in that. So now we will briefly check into the Open Charge Point protocols and what is it is, why it is really needed in the electrical vehicle supply equipment or the charging stations. The Open Charge Point Protocol, or simply called as OCPP, is an application protocol which is used to communication between the electrical vehicle supply equipment and the central management system. So we know the charging station is to provide the power to the electrical vehicle, but what is this central management system is a kind of a backend server which will handle the user entity and how much the charges, how much energy has been used by the consumer on different charging station, and based on that, the billing will be generated. So these database will be maintained by the central management system. So it is the Open Charge Point Protocol is established by Open Charge Alliance. It is established by in 2009, and since it has the advantage like it is designed to be the free open source and also interoperability support, it becomes a global benchmark for throughout the EV industry to adapt the OCPP in all the charging station, I would say. Okay, so does OCPP really need in the charging station is a question, because when I have a private charging station which can directly connect to the electrical vehicle, then there is no need of charging the OCPP protocol. But really, when we have the public infrastructure installed, the EVSE, then we need a communication back to the backend, which is supported by this Open Charge Point Protocol. So I would say the Open Charge Point Protocol is not an option for the public infrastructure, and also I would say it is recommended for the private infrastructure as well, private charging station as well. Why? Because we need a more and more distributed net charging infrastructure. For that, even the private contributor to the charging infrastructure, which will help the whole EV industry, so or the EV segment. So when the private charging station is not in use, it can lend for the public access, and based on that, you can boost the EV segment or the charging segment. So OCPP has been developed in the with the multiple versions, starting from the V1.4 and 1.5, which are already obsolete, which supports a different messaging format, which we will going to see in the next slides. Currently, we have the support of version 1.6 and version 2.0.1. And with respect to current presentations, we limit the scope of version 1.6. Okay. If you are new to the electrical vehicle supply equipment of the charging, these are all the abbreviations which we'll be going to use in the following slide. So it would be helpful if we can see these are the observations. So CP meant for the charge point, and CPO is a charge point operator who can handle the database of the maintenance of the central system, and CS is the backend system, which is central system, and then ID tag. Unique identification used to identify the user, maybe the access card where we can read the ID tag. And OCPP is Open Charge Point Protocol. Then there are two messages which is framed by the OCPP. The PDU is a protocol defined unit, and RPC, which we will see in the next slides. Okay. The profiles and messages. The basic communication between the central system and the charge point are based on the predefined protocol defined unit, or simply the PDU messages. So these are the basic building blocks between the communication between the charging station and the central system. So there are approximately the version 1.6 supports 29 messages. We are not going to see all those messages because of the time constraints, but these messages are grouped into a profile based on the features and functionality. Here are the list of profiles supported by the version 1.6, the core profile, which is the mandatory profile, basically handles all the messages which are required for the charging and stop charging, etc. Apart from that, we have the local authorization list message, and which is mainly to authorize when there is no connection between the central system and the charge point because of the network issue of anything. And then the charge point can take action like it can authorize the user if the user has been already authorized and it has the validity tag. Then we have the firmware management profile, which is for the over-the-air update of the firmware for the charge point itself. So we will not see all these profiles, but we limit to the core profile and its messages. Here are the list of the messages which is supported by the core profiles. And again, we are not going to see all of them, but at least we will pick the messages which are essential for one complete charging cycles. So we will have a look into the authorize, boot notification message, meter values, start-stop transaction, and then remote start-stop transactions. Okay, so boot notification is the PDU message, which is the first message which charge point sends to the central system. So central system will enumerate or discovers there is a charge point available in the network using the boot notification message. And after a startup or the reboot, or the charge point initiate the communication with the central system. So the boot notification message carries the following informations like charge point model, charge point vendor IDs, and then the ICC ID, IMSI ID. So no other PDU message should be sent without acknowledgement or of the boot notification or the acceptable of a central system. Okay, when the user wants to get into the access of the charging station, first he has to get authorized. So the unique identifier authorized unique identifier is used for the authorization purpose. This unique identifier is read from the access card using RFID on the charging station. Otherwise, there is other mechanism like when the mobile applications like smartphone mobile application. Otherwise, the web browser is used to kind of a virtual ID directly. It can start communicating with the central system, and then central system will authorize the user. So when the when the user get authorized, then he can able to start charging its vehicle after connecting the connector into the EV from the charging stations. So once we have authorized, the user get authorized, then the charge station, after connecting the cables, the charge station can deliver the power to the electrical vehicle. After that, it can send a message, confirmation message to the central system that start transaction has been already started by sending the start transaction PDU message. Okay, once we have started the transaction, then if the battery gets completed, otherwise if user want to interrupt the stop the charging, then he can hit a button on the charging station. Then the charge point can terminate the power supply to the electrical vehicle. After that, it can send a stop transaction PDU message to the central system to notify that a transaction has been already stopped. Okay, so far we have seen the stop transaction and boot notification, all these messages which originate from the charging station to the central system. But there is a way, as I said, when the user wants to start charging, he can request to the central system using the mobile application or the web browser. Then the charging station can request start transaction message to the charge point. So this is used by the two messages called the remote start transaction and remote stop transactions. Upon receiving this remote start transaction, stop transaction, charge station can decide whether it can start or stop based on the local environment, like whether the power supply is available to deliver the EV or else the cable is connected. So once it is done, then again it should follow the same process of what we have seen in the previous slide, like start transaction, stop transaction. So one of the peculiar case with here is the remote stop transactions. It is not necessary that these remote start and stop has to be always the pair. Even if the local charge station sends a start transaction, those transactions will be available on the central system. So remote stop transaction message can be sent from the central system for already started a charging session. Okay, there are some cases where malfunction of the cable retentions, like after authorization, the user has to get the cable and then connect to the chargers. If there is any malfunctions happens with that, then he can request the CPU operator, the CPU operator, so that the charge point operator can send an unlock connector message from the central system to the charging station. Okay, so we have seen the start transaction, stop transaction, which has the which carries the informations like which connector it has started, and also at the time of starting the meter values are sent, and also at the time of stopping the meter value has to be sent. So based on this stop and start transaction meter values, the billings are generated, how much the power has been consumed. Apart from that, in the start and between the start and stop transaction, so the charge point may collect the information of the current meter readings and also send it to the central system. The purpose is like the central system may have the kind of graph mechanism to plot how much the charging is consumed, and for those purpose it is the meter values are used, and the meter values carries the values like a connector ID and the current meter value. So it is like frequently sent from the charging station to the central system. So we have seen so far the specifications, what are the basic messages of the predefined unit messages, and these predefined unit messages are not sent to central system directly. Instead, it will be wrapped into a or encoded into a wrapper called a remote procedure call messages. This carries a message type and then unique identifier and the payload of the OCPP PDU message itself. So the message type are primarily categorized into three types. One, the call to send a request, and call result is to reply or getting the response for the call message, and then call error if in case of any error or the failure with the reasons. The OCPP specification is mentioned that there should not be a new call message originate either from the charge point or central system unless until the previous call message has been responded or timed out, which means there will be only two call messages exist in between the charge point and the central system at any instance, one originated from the charge point, another originated from the central system. And there should not be new call message should be started before the response or the timed out. So we have seen the message frame, and here we will see the example for the call request message frame and also the call response message frames in details. So we have the message type of 1 byte which carries constant 2 for the call request, and we have the message ID which is used for the purpose of identifying the message itself. So it should be the unique identifier of any string of 1 to 32 bytes. After that, the action which will carry the PDU, what is the purpose of the PDU, like the boot notification or a start transaction or stop transaction, and then the payload itself. The payload what we have used in this presentation is there are two types of payloads supported or PDU message format supported in the OCP 1.6. One is the JSON format, and another one is SOAP. But with the later version or the version 2.0, only we have the JSON format. So throughout these slides, we have used only the JSON format. So here we can see the example for the boot notification, and then the charge point vendor IDs and the models has been sent on the call request, and we will get into the call response as the message type constant 3, and then the unique message identifier which is used to send for the call request here. The same should be here, so it can match which packet the response has been received. Then we have the response JSONs for the payload for the boot notifications. So we have so far seen what is the specification, what specification has said about the message format and then the message sending the wrapper. But how could we really visualize into the complete charging station? So we will see here one of the example use cases, because we cannot able to cover all of them, but here we have mentioned one of the use cases, like how the user interaction between the EV and the EVSE, and then the EVSE to charging station uses the OCPP PDU messages. The first, the user has to get the access. For that purpose, he shows the access card to the EVSE. Then the EVSE, we will have a card reader like NFC or the RFID reader, which will read the ID tag. Once it read the ID tag, it will send the OCP authorized request message to the central system, and then central system will check all the database, like navigating whether the ID tag is matched and it is already in the valid state, or else it's expired or blocked and all these states. So once we will take it to the happy path here, like the ID tag has been already matched, and then we will get the response like authorized. So once authorized, the user is able to the connector is released from the EVSE, so user can able to pull in the connector from the EVSE and then connect to the EV. Then once the cable is connected, user can able to press a button of the start button available on the charging station. Once the start button is pressed, EVSE then release the circuit for delivering the energy, and then it can send the OCPP message that start transaction message that transaction has already started with the meter readings when it was about to start. So one successful transaction, then the meter values is continuously sent from the EVSE, like how much consumption by the EV, until the stop transaction or the complete charging cycle ends. So when the user wants to interrupt or stop the charging, then he can hit the button on the stop charging button on the EVSE. Then the EVSE will shut down the power to the EV, and then it can send measure the energy meter, what is the last reading of after shutting down, then it can send the OCP message stop transaction to the central system. After that, cable can be disconnected and inserted to the EVSE. So we have seen one complete charging session use cases for how the user interacts with the charging station directly for the start and stop chargings. We will have another example which showcase here the user can directly interact with the central system instead of EVSE. So if a user can have a web authorize or the smartphone which can able to interact with the central system, then the virtual RFID is used here to communicate with the central system, and then the central system will check the database and then it will authorize the user. Once he has been authorized, the EVSE will unlock the connector, so the connector can be, the user can pull in the connector and connect to the EV vehicle. After that, the user can start the transaction or the start charging by pressing a button on the application, and it goes to the central system, and then central system will send a message, remote start transaction message. After that, the EV has to solely responsible to decide whether it can deliver the power to the electrical vehicle based on whether the good power is available to that, and also the cable is connected and the proper things of all this. So once charging is started, then it can send a start transaction message to the central system. It carries the same the cycle what we have seen in the previous slides, like it sends meter values frequently. After that, when the user wants to stop, then he can request the central system using a web application or else the mobile phone smart application. Then the central system will send the remote stop transaction. After that, the EVSE will shut down the power and will do the stop charging sequence. After that, it will send a stop transaction PDU message to the central system. And finally, the EVSE or the user can disconnect the EVSE the cable from the EV and to the can connect back to the EVSE. Okay, so far we have seen how the OCPP specification messages appears and how it has been wrapped into RPC message to communicate with the central system. So now we get into how the protocol is being implemented in the Zephyr RTOS. Since OCPP is application protocols, so it can coexist with the MQTT, CoAP and other application protocols. The OCPP sends a message using the socket APIs, especially the WebSocket APIs, to the central system in any of the network interface like Ethernet, Wi-Fi or the modem. And then the OCPP exposes a public API for the application use case. So application can directly use those APIs to send data to the central system or back and forth. Okay, now we will look into the how OCPP stack is implemented in the Zephyr RTOS. So as I said, we have native, at the bottom we have the native WebSocket implementation of the Zephyr, and then in the top we have the application which consumes the OCPP consumer APIs. So from the bottom up, we have the RPC message format, and above that we have the JSON PDU format. Then we have the list of profile implementation, the core profile which has the start transaction, stop transactions, and then we have the interesting one which is the key management in the right side. What is this key management is, we have the key value pair which is maintained or used to communicate between the charging station and central system. If, for example, so we have the meter values, it has to be sent frequently, but how much time it has to send, so this is configurable using the key value pair. Apart from that, we have heartbeat messages, so then timing between the heartbeat, how much time it has to send, it can be read from the central system and also can be changed by from the central system, and for that purpose we have the key value pair. Then we have the OCPP internal implementation which carries the socket connection and the reconnection handlings. So user has nothing to do with the when the internet or the socket get disconnected, the OCPP stack itself can able to reconnect, establish the connection, and we have the user notification handlings. For example, so when the central system sends some of the requests to the charge point, then it has to notify to the user like start charging, stop charging. Otherwise, even the internal request from the OCPP, like the meter value, the frequency has to read from the application, that will be used by the user registered callback in the init functions. Now we will look into the API which is exposed to the consumer. The first one is Open Charge Point, the OCPP_init API, which is supplied with the charge point information and central system information. So, the charge point model, vendor, and the number of connectors are the mandatory information which needs to be filled to the for the charge point information, and then central system information like IP address, which is a resolved one, and then port and WebSocket URLs are supplied here. So before initializing the OCPP library, the network interface should be already up and running, because once we call the OCPP init, then it will try to establish the socket connection with the central system, and then it sends the boot notification message. Then we have the pair of session handling APIs, so OCPP session open and close. So each connector, then the charge point may support n number of connectors, and each connector should have open a new unique session handling before any of the further like start transaction or the stop transaction API is used. The session management is sole purpose of internal to the stack and nothing relevant to the specifications. Okay. So from the application, so when it wants to get authorized, then it can use the OCPP_authorize API, which carries the ID tag as an input, and then we will get the status as a response, and the status may carry the invalid, accepted, blocked, etc. So once we have the response with the OCPP_auth_accepted, then the user is allowed to start charging. So we have this OCPP_start transaction messages, like when charging station has already started delivering the power, it can read the energy meter values, and then it can send the start transaction message to notify that the central system transaction has been started. So it is binded with the connector ID, and then what is the energy meter at the time of start. Then once we have the the transaction has been started, then user callback, the register callback and the init function will be called from the stack using the reason like get meter values, just to read the meter values. So it is recommended that this callback function needs to be written as quick as possible. Like the meter value should not be read in the callback itself, maybe another parallel thread which can read the and can share between the this callback function and the another thread. And the other reasons may be like start charging and stop charging, which is originated from the central system. Once the complete charging cycle has completed, then we can use the application may use OCPP_stop transaction with the reading from the energy meter. Okay, we have seen so far the OCPP, which is used primarily between the charge point and the central system. But does EVSE really complete with that? Not really, because we have the real handshaking between the charge point and the electrical vehicle and to deliver the power, which is mentioned by the standard IEC 16851 and ISO 15118. Unfortunately, these specifications or the standards are not open, and we can see very overview about that. So we have two mechanisms for handshaking. One is for the control pilot, and another one is proximity pilot. Control pilot is mainly used for the communication to negotiate the charging level of the car and the charging station, and then proximity serves for the cable detection and current limitation. So OCPP, I would say the OCPP part will cover 40 to 50% of EVSE. The other part is still covered by the application with the IEC implementation. So if you will see the use cases here, once a user got authorized, then it will be in the state of A1, which the control pilot the values is the voltage level in the 12. After that, the cable is connected to the EV, then it will drops to the 9 voltage. By detecting the cable is connected, then the EVSE can prepare for the charging, and it will communicate to, or it will notify the electrical vehicle that the charging is it is ready to power the charging, deliver the charging. So the PWM signal is used with the 9 voltage. After detecting the PW signal by the EV, then EV will pull down the control pilot voltage to the 6 voltage. So the charging is started, and then we have the we can send the start charging OCPP, and then we have the EVSE stopped once we get full charging, and we will enter into the state like C1 and stop charging. So once the user presses the stop button, it can come into the default state, the B1, and then the cable can be disconnected, so it will go to the state A1 or 12. Okay. So we are almost come to the end of the presentation. Here the state like the OCPP is currently under review, and it will be get merged after a review is completed. Then currently we have 1.6 core profile is supported, and then the future work is the TLS support and 1.6 optional profile and 2.0.1 supports. Thank you. Do you have any questions?
Yeah, 1 second.
Hi, thank you for the presentation. This was really clear to me. The diagrams really helped in terms of explaining each of the steps and in order for this overall charging workflow. Okay. One thing that perhaps isn't so apparent is really this start transaction phase, right, whereby the charge point equipment sends this request to the central system. So is this a required step in order for the vehicle to begin charging, or is this purely to send some information to the central system to like notify them? Okay. Is this a critical part, or is this a blocking operation, or is this like sort of?
Okay. So the main purpose of OCPP is, as I said, it has to communicate to the central system so that central system know how much the power has been consumed by the user, and then it will generate the billings. So for that, the start transaction should be notified to the central system, and then also the stop transaction has to be notified to the central system with the meter values. So it can the central system will calculate based on how much the start of the energy meter and what is the end value of the energy meter, and based on the difference, it will translate into the billings.
Okay, thank you for clarifying.
Hello, very good presentation, and I would like to extend your topic about ISO 15118 a little bit.
Yep.
So that standard is more about encryption safety, and one major part of it is plug and play.
Okay.
So yeah, but I don't see any content on your slides, and I'm curious about does your company support such a feature? And when we do plug and play, we find which is so difficulty to connect your charge point to the vehicle. So you have to let your charger to notice who is using it, and which account it belongs to, and when to start chargers. So by that standard, the ISO 15118 provides a very complicated handshaking certification procedure there. So how does Zephyr helps you on it, or doesn't have at all?
Okay.
Thank you.
So since it is a closed source, we cannot able to explain much into the current presentation. Otherwise, we have implemented to one of the customer the EV with full blown with a specification of 11518. Yes. Is that answers your question?
I think it's more than that, but I can contact you with you later.
Sure. Thank you.
Okay, thank you very much.
Oh, there is one
there's
more.
one more?
Yeah.
Yeah, sorry. I did.
Hey, I was just wondering, how often does the meter pull back to the central system, and also what happens if you miss the stop transaction from the central system? I don't want to end up like getting free energy from this charge point for forever, but I was just curious how OPP or OCPP handles that.
Okay. For your first question, it is configurable values that how often the meter value has to be sent. As I said, there is a key value pair which is read from the central system, and also it can modify the values. So based on that, the meter values is been sent. And regarding the last question, it's stop transaction has been missed by the central system, you mean, or? Because the
No, if the charge point misses the stop transaction from the central system.
Okay, so central system does not send a stop transaction message to the charge point. The charge point is the one which will notify the central system that transaction has been ended with a stop transaction message.
Got it.
Okay.
Thank you very much.
Thank you.